Chapter 2: Internal Energy, Work, Heat, and Enthalpy. Section 2.2: Work. There are many types of work, but in thermodynamics, we will focus on the expansion/compression work. In the last two chapters of thermodynamics, we will briefly introduce the electric work. So now let's get back to the expansion/compression work. For convenience, we usually call this expansion work. Expansion work can be calculated using this formula: negative integral external pressure dV. The proof is as follows. Let's look at a system over here in blue color with a pressure P and volume V. And this is a piston. We're exerting a external force F to the piston, and this is going to compress the system. Now if we move this piston for a distance of dx, then the amount of work is F dx. If we move a finite distance delta x, then the amount of work is simply F times delta x, if this F is constant. But what if the force changes during the displacement? Then we'll have to resort to calculus. Work is the integral of force times dx, and this allows this force to change when x changes. Now let's look at this system in blue color with the pressure P and volume V. When this is compressed, work again is the integral of force times dx, and force is the external pressure times this area A. That's by the definition of pressure. And then we can replace force with P external times A. We got this equation. And remember, A times dx happens to be the volume of this displacement, and this is simply dV. This is the change of volume. And then we have a nice equation. Work is equal to the integral of P external dV. Now you may ask why there's a negative sign here. This is because when we define expansion work, if work is done on the system, we say work is positive. If work is done by the system to its surroundings, we say work is negative. We add this negative sign to emphasize that expansion work is positive if work is done to the system, and W is negative if work is done by the system. Again, the equation for expansion work is negative integral P external dV. So there are two things we need to pay attention to. The first is the sign. We have this negative sign here. The second thing is the subscript. P sub ext is the external pressure, not the system pressure. So it's possible for the system pressure to be different from the external pressure. In that case, well, we'll have to use the external pressure to calculate the amount of work. Work is transitory. That means it's not associated with the state of the system, but associated with the entire process that results in the change of the state of the system. So that means if you go from state 1 to state 2, and if you know everything about the initial state, state 1, and everything about state 2, the final state of the system, it's still impossible for us to calculate the amount of expansion work. We'll have to know the more information about the process that connects state 1 and state 2. So again, given only the initial state and final state of the system, we cannot calculate the amount of work. Let me give you an analogy the analogy is this, what's the number of steps you have walked today? Now I'm going to give you some information. So initially you are in your dormitory. At the end, your final state is also in your dormitory. Now my question is, how many steps have you walked in this day? You know the initial state, you know the final state. Actually, they are the same, but you cannot actually, we cannot tell how many steps you have walked, between the initial state and final state. You could have just stayed in the dormitory for the whole day, and you just lie on the bed, and then the number of steps is just 0. Or you can just walk like 6,000 steps to somewhere else and then come back with 6,000 steps. Then you have walked a total of 12,000 steps in that day between the initial state and the final state. All right. If work is done, it's always between two objects. If we're talking about the work of the system, we have to understand this equation. The work done to the surroundings is the opposite of the work done to the system. So W surroundings plus W system is always 0. And over here there's a animation of a so-called isothermal expansion of an ideal gas. This isothermal means the temperature is constant. I'm gonna just play this isothermal expansion over here. So we heat it up, the gas expands. So you can see the PV curve here. But the temperature is constant. You may wonder, how can this temperature to be constant? Let me explain. When we have ideal gas, that means there's no attraction, no repulsion between gas particles. The potential energy is always 0. And we know temperature is a measure of kinetic energy. So somehow, if the kinetic energy is constant, then temperature is constant. So how can we have a constant kinetic energy situation here? Well, when we heat it up, yes, energy flows into this system in the form of heat. But at the same time, the system expands, right? So when the system expands, it can do work to its surroundings. It's pushing its surroundings. So the system loses energy in the form of work. In summary, it gains energy in the form of heat. It loses energy in the form of work. And it's possible for the amount of work and the amount of heat cancel. In that case, the internal energy of the system remains constant. And because internal energy is equal to potential energy plus kinetic energy, that means the kinetic energy remains constant. There's no temperature change. So again, in an isothermal expansion of an ideal gas, delta U is actually 0. That doesn't mean Q is 0 or W is 0. It simply means Q and W cancel each other. And when we heat it up, Q is greater than 0, and then we know W is less than 0. Also, we can see in this animation, the system expands against its surroundings. That means work is done by the system to the surroundings. Therefore, work is negative. Now let's look at several numerical examples to see how expansion work can be calculated. Example problem 2.2.1. Calculate the work involved in the following 3 isothermal processes, and then compare the results. A follow-up question is, how can we maximize or minimize work? Now let's look at A. A 20-liter ideal gas with 4 bar pressure expands to 80 liters against a external pressure of 1 bar. So if the gas expands against 1 bar, in the end the system pressure will drop from 4 bars to 1 bar. 1 bar is going to be the final pressure of the system. Now let's compute work. Work is negative integral P external dV. Again, 2 things. First, you need to remember this negative sign. 2, it has to be external pressure, not the system pressure. What's the external pressure? It's 1 bar. We plug in the numbers. We have the lower limit and upper limit for the integral. We do the calculation. It's negative 60 bar liter. This is negative because the system expands, it does work to the surroundings. B. A 20-liter ideal gas with 4 bar pressure first expands to 40 liters against 2 bar external pressure, and then it further expands to 80 liters against 1 bar external pressure. So remember, there are 2 steps. In the first step, external pressure is 2 bar. The second step, the external pressure is only 1 bar. So we have to compute the amount of work for each of the 2 steps. In step 1, the system expands from 20 liters to 40 liters. The external pressure is 2 bar. We evaluate this integral, we get negative 40 bar liter. In step 2, similarly, we use this equation, negative integral P external dV. What's the initial volume in this step 2? It's 40 liters. Final 80 liters. And this time, the external pressure is only 1 bar. Evaluating this integral, we get negative 40 bar liters. And we can sum it up. This work is additive. So the amount of work done by the system is 40 bar liter in the first step. And it happens to be also 40 bar liter in the second step. We add them up, we get negative 80 bar liters done by the system to the surroundings. So in the first example, this is a 1-step process. Work is done to the surroundings. The amount is 60 bar liter. In the second, this is B example. This is a 2-step process. The system does 80 bar liters to the surroundings. So now we wonder if we have more and more steps, should this number keep increasing? Well, we'll see. Again, we examined 2 different processes of the expansion of ideal gas. A 1-step process versus a 2-step process. In the 1-step process, we get negative 60. In the 2-step process, we get negative 40 plus negative 40. Now let's use a graph to visualize these 2 different processes. Alright, so what I'm going to do is I'm going to plot this P external versus V. Again, this is P external versus V, not system pressure versus V. So if you have some other copies of PChem textbooks, so occasionally you can see P versus V when they are trying to visualize expansion work, and that's inaccurate or incorrect. So again, it has to be P external if you are interested in the expansion work. Now the system expands from 20 liters to 80 liters, and the external pressure is a constant 1 bar. So you can see I'm gonna go from 20 liters to 80 liters with a constant 1 bar pressure. And the integral is simply this area, and it's pretty simple. The height is 1 bar, while the width is 80 minus 20, 60 liters. So this area is 80 bar liters. And remember, the system does work to its surroundings, so it should be negative 60 bar liters. Alright, now let's visualize the 2-step process. So in the 2-step process, we first expand this gas from 20 liters to 40 liters against a 2 bar external pressure. So this 2 bar external pressure, so we are looking at this rectangle in the first step. In the second step, the expansion is against 1 bar pressure. The volume change is from 40 to 80. So this is the second step. Again, there are 2 rectangles. The first rectangle is here. The second rectangle is here. And if you sum up the areas of these 2 rectangles, you will get negative 80, considering the sign for the work done by the system. Now let's compare these 2 graphs. What's the difference? Okay, if you look at the 2-step process, you can see we have some additional area. So this does not appear here. It's here. So that's why in this 2-step process, the system does more work to the surroundings. So this part is 20. Alright, so we have 60 here, we have 20 here, and then we have a total of 80. And again, we wonder if we have more and more steps, can we just, get more and more work? So here's another example. In this example, again, a 20-liter ideal gas expands from 20 liters to 80 liters. The system pressure is 4 bars, But now over here, this is kind of strange. The system expands against a P external, and we're going to assume P external is equal to P. The external pressure is equal to the system pressure, also in an isothermal process. Now let's look at the integral for the expansion work. Negative integral P external dV. Given this condition, P external is equal to P, we can replace this P external with P. So we're going to just integrate this, and remember, it's an isothermal process. If it's isothermal process, when we integrate this, we can just express pressure as a function of volume easily. Its pressure is just nRT over V, and then T is a constant. So that's why we take this nRT out of the integral. We just need to integrate 1 over V dV. That's the logarithm of V. So in the end, we get a interesting formula here that involves the logarithm. It's negative nRT times the logarithm of final volume over initial volume. We do not know the temperature, but we can we can calculate nRT by using PV equals nRT, and it's isothermal, so we can use initial PV or final PV. So nRT is equal to initial PV or final PV. It does not matter. Let's use initial PV. It's 20 liters times 4 bar, so that's 80 bar liters. Therefore, we can replace nRT with 80 bar liters. Work is negative 80 times Ln4. 80 over 20, that's 4. So bar liters. And we just calculate the logarithm of 4. I think it's roughly 1.4. We do the calculation. We get negative 111 bar liters. And later you will see this is the maximum amount of work the system can do to its surroundings. Remember, in the previous examples, we had 60, we had 80, and now it's 111. And this is the maximum amount of work the system can do to its surroundings given this initial condition and also final condition. Now you may wonder, if the external pressure is equal to the system pressure, they cancel. How can the system expand? It's just because you can somehow imagine, they are not exactly the same. What if the system pressure is equal to external pressure plus 10 to the power of negative 1,000 times P external? Then if you have this equation, you can see the system pressure is slightly greater than the external pressure, so that the system can expand. Meanwhile, P external is roughly equal to P. So it seems contradictory, but hopefully using this example, you can see P is greater than P external. At the same time, P is about the same as P external. So we can still use this equation to compute the amount of work. Now we have worked on 3 numerical examples. If we have just one step process, P external equals 1 bar, we get negative 60. If P external is equal to 2 bar in the first step, 1 bar in the second step, we get negative 80. We can set P external to be P in this entire process, and then we get negative 111 bar liters. And later we'll see this is the maximum amount of work that can be done by the system given the same initial and final states. Now let's look at more numerical examples. This time still isothermal, but now let's look at compression. Alright, we'll look at compression. So the initial state of the ideal gas is 80 liters, 1 bar pressure. We are going to compress it to 4 bars and 20 liters. We need to know what is the external pressure, because again, in the formula for work, we need to use negative integral P external dV. Now we plug in the initial volume, final volume, and also external pressure. The result is 240 bar liters. Now we're going to do a 2-step process. First, we compress this system against a external pressure of 2 bars, and then the final system pressure in this step is going to be 2 bar. We're not done yet. In the second step, we increase the external pressure to 4 bars. We keep compressing the system until its final pressure reaches 4 bar, and the final volume is going to be 20 liters. Because there are two steps, we'll have to calculate the amount of work in step 1 and then step 2. In step 1, P external is 2 bars. The initial and final volumes are 80 liters and 40 liters. Evaluating this integral, we get 80 bar liters. In the step 2, again, we use the same formula, but the external pressure is actually higher. It's 4 bars. The initial and final volumes are 40 liters and 20 liters. And solving this integral, we get also 80 bar liters. The total amount of work is W1 plus W2. The result is 160 bar liters. So you can see in step 1, we have 240 bar liters. In step 2, we have 160 bar liters. It seems that if we increase the number of steps, we get less and less amount of work. So is there a minimum for this compression work? Now again, let's visualize these two processes. In the one-step process, the external pressure is 4 bars. So I'm going to plot this P external over V. The initial volume is 80. The final volume is 20 liters. So it goes from 80 to 20. The external pressure is 4 bar. So I'm making this rectangle. The height is 4 bars. The width is 80 minus 20, which is 60. And we can easily see the area of this rectangle is 4 bars times 60 liters. Therefore, it's actually 240 bar liters. The surroundings does this amount of work to the system. Now, what if we use a two-step process? So in the first step, we use only 2 bar pressure to compress the system from 80 bars to 40 bars. We get a rectangle with an area of 80 bar liters. And then in the second step, we use a 4 bar external pressure to compress the system from 40 to 20. Again, we get 80. If we sum it up, you get 160. This is smaller than 240 because you can see this part is missing. Okay, this part is missing. How much is this? It's simply just 240 minus 160, so this part is missing. This part is 80. Now let's look at another compression process. This time, still we have the same initial and final states for the system. The initial state is 80 liters in 1 bar. The final state is 20 liters and 4 bars. But this time, we're going to compress the system in a process that P external is equal to P. So again, we use this formula and we can replace P external with P. Alright, and then pressure is nRT over V. This is an isothermal process, so temperature is constant. We take nRT out of the integral and we need to evaluate the integral of 1 over V dV. That's the logarithm of V. So we have logarithm of 20 minus the logarithm of 80. It's just the logarithm of 20 over 80. So we know how to compute nRT because PV equals nRT. We'll just use initial state. PI is 1 bar. VI is 80 liters. So nRT is 80 bar liters. And throughout the entire compression process, nRT remains constant because this is an isothermal process. Now we just plug in 80 here. We'll have to evaluate 80 times the logarithm of 4. We get 111 bar liters. Alright, so again, you know, we get this same number when we do the expansion of the gas. If P external is equal to B, we get 111. Now we're doing compression. If P external is equal to P, we still get 111. Again, how can we compress the system if P external is equal to P? Well, somehow you can just imagine P is slightly smaller than P external. For example, P is just P external minus a very small number times P external. Then this way we have P smaller than P external. The system can be compressed. At the same time, we can say P is equal to P external because this term, you know, 10 to the power of negative 1,000, it's negligible. So we studied 3 numerical examples for the compression process. one step, two step, and then the third one is P external equals P. So in the one step process, when we compress the system against a 4 bar external pressure, the amount of work done to the system is 240 bar liters. What if we use 2 bar external pressure first, going from 80 liters to 40 liters, and then we use 4 bar pressure, going from 40 liters to 20 liters. Overall, we get 160, so these two numbers are different. And then finally, we say, well, why don't we just make sure P external equals P, and then we have 111 bars. And this number is actually the minimum amount of work that is done to the system, given the same initial state and final state. The initial state is 80 liters, 1 bar. Final state, 20 liters, 4 bars. So this is just a summary. There are two tables. One is for expansion, one is for compression. So if we look at expansion, we studied one-step process, two-step processes, and over here we have P external is equal to P. Over here, same thing, one step, two step, P external equals to P. So over here you can see negative 60, negative 80, and then negative 111. Over here, 240, 160, 111. So a couple things we need to kind of just mention. One is this: work is transitory. The amount of work depends on the process. So if you are given the initial and final state of the system, it's impossible to compute the amount of work unless you know more information about the process. What information? This P external. So for this process, we know P external is just 1 bar. Over here, we know there are two steps. In the first step, P external is 2 bars. In the second step, it's 1 bar. Over here, we also know P external is equal to P. And then we know ideal gas law, so P is nRT over V. So somehow we know the information about the external pressure. Alright, that's the first thing we need to know. Like, we cannot determine the amount of work unless we know more information about the process other than the initial and final states. And also, if we do this, P external equals to P for expansion, we get the maximum amount of work that can be done by the system, 111. So same here, if we use P external is equal to P, we get the minimum amount of work that can be done to the system. That's also 111. This is not a coincidence. It's just because when we integrate the amount of work, in both cases, here and here, we have P external is equal to P, and basically we're just integrating negative integral P dV, and the upper limit and lower limit of volume over here are 20 to 80 liters. Over here it's 80 to 20 liters. That's why these two numbers are the same. They just differ by the sign. One more numerical example about some cyclic processes. So we're gonna do, like, for example, we're gonna do expansion and compression so that the system gets back to this its original state. Now let's look at one example. The initial state is 20 liters 4 bar. We first expand to 80 liters and 1 bar, and then compressed back to 20 liters and 4 bar. The expansion is 1 step, the compression is also 1 step. So we did this calculation before, it's negative 60. We did this 1 step compression before, it's positive 240. So when the system gets back to the original state, well, there's a total amount of 180 bar liters. This amount of work done to the system. It's kind of strange. The system gets back to its original state. How can this amount of work be done to the system? Well, it's simple. When a system gets back to its original state, well, it should have the same energy. The initial and final internal energy should be the same. And how can this amount of work done to the system? Well, the system must have lost energy in the form of heat. So at the same time, it must have lost this amount of heat. Now let's look at another example. So again, the ideal gas first expands and then being compressed. 20 liter ideal gas 4 bar pressure expands to 40 liters and 2 bar against 2 bar external pressure, and then expands to 80 liters and 1 bar against 1 bar external pressure. So two-step expansion followed by two-step compression. So what's the total amount of work? Actually, we computed this two-step expansion. It's negative 80. We computed the amount of work in this two-step compression, which is 160. So together, it's 80. So in this B example, this B example, we had two-step expansion followed by two-step compression. Overall work is done to the system. The amount is 80 bar liters, and we know this system must have lost the same amount of energy in the form of heat. One more cyclic process example over here. Still 20 liter ideal gas, 4 bar pressure expands to 8 liters and 1 bar. But we're going to ensure this condition, P external is equal to P, and then followed by the compression, P external is still equal to P. So we learned in this first step it's negative 111. In the second step it's positive 111. They cancel. So overall the amount of work is 0. So Q is also 0 in this cyclic process. So in summary, we covered 3 different cyclic processes. In the first two, net work is done on the system. I want to show you in A, this amount of work is done to the system, 180. In B, 80 bar liter is done to the system. Alright, but in C, it's just 0. And I want to remind you that internal energy is a so-called state function. It only depends on the state of the system. So that means when a system undergoes a series of steps and gets back to the original state, the internal energy should be the same, right? Same state, same internal energy. However, work and heat are not state functions. They depend on the processes. So in this 3 different cyclic processes, we get 3 different numbers for work. Alright, and finally I want to just talk about this process C a bit more. The net work is 0, the net heat is also 0, and overall there's no net change to the system or its surroundings. So we want to say this, you will learn later, the in this C cyclic process, the entropy of the universe remains constant because there's no change to the system. There's no change to the entropy of the system, and there's no change to the surroundings. Therefore, there's no change to the entropy of the surroundings. Overall, the entropy of the universe remains constant. And later we'll say this process is a reversible process because if the entropy of the universe increases, well, we cannot reverse it because the reversal will result in the entropy decrease of the universe, which is in violation to the second law of thermodynamics. And later we'll see, as long as we hold this equation, P external is equal to P in expansion and compression, we say, well, this kind of processes, whether expansion or compression, we call that reversible. Again, if P external is equal to P, we're not going to increase the entropy of the universe so that we can reverse it without violating the second law of thermodynamics.